Hey guys, welcome back to my channel. I'm Advaith Pillai, and today we are going to be continuing with logarithms, and this is going to be part 2. So let's begin. So, yesterday we looked at some of the properties of logarithm, such as product law, quotient law, power law, and the change of pace theorem. So, today we are going to be looking at some important results in logarithms. So, first of all, we have log a to the base a gives 1. So how this works is if you convert it into indicial equation, you get it as a raised to 1 is equals to a, which is true because anything raised to 1 is the number itself. Therefore, this is one of the important logarithmic properties. Okay, moving on to the next one. The next one says that log 1 to the base a is equals to 0. So if you have log 1 and the base is any number, the answer should be 0. So let's again convert this into an indicial equation. This becomes a raised to 0 is equals to 1. So this holds true again because anything raised to 0 is 1 according to the properties of indices. Here a is not equals to 1 as we had discussed during the definition of logarithm where a is greater than 0 but it is not equals to 1. Now let's look at what happens if a is 1. Let's say a is 1, okay, and b is also 1 as in this case. So if we convert it into indicial equation, so this becomes, first of all, let's take the solution as x. Therefore, 1 raised to x is equals to 1. Now the problem here is the value of x can be any imaginable number. It can be 2, it can be 3, it can be 400, it can be 7,000, etc. Therefore, the answer of this logarithm is not defined. Okay. Now let's look at other examples where a is 1 but b is not 1. For example, let's say we have log 5 to the base 1. Okay. Let's convert this into an indicial equation. So this becomes 1 raised to x is equals to 5. But this is clearly not possible because if 1 is raised to the any power, the answer is always 1 because 1 multiplied by 1 multiple times is always 1. Therefore, a is never equals to 1. Therefore, in the definition, it was written as a is not equals to 1. So, this is the reason behind it. Okay. Now, let's move on with the two types of logarithms. So, the two types of logarithms are natural and common logarithms. So, first, let's look at natural logarithms. The logarithms which have the base e, Euler's number, are known as natural logarithms. It was discovered in 1614 by John Napier. So the value of E is 2.71828 dot. It is a non-recurring and non-terminating decimal number. It is an irrational number. So this logarithm is a natural logarithm because the base is E. And this can also be denoted by ln of x. ln basically means log to the base E. This is log to the base e. And then the x comes in, and therefore it becomes log x to the base e, which is the same thing as this. So this is how this works. Now, another important thing to note is that there is a difference between Euler's number and Euler's constant. Okay, so please make a note of that. Yeah, so this is the natural logarithms where the base is e, which is equals to 2.71828 and it goes on forever. This type of logarithm is used more in physics and chemistry. In mathematics, we use something which is known as common logarithm. So the logarithms which have the base 10 are known as common logarithms, and it was discovered a year later in 1615 by Henry Briggs. So therefore, base 10, any logarithm which has the base 10 is a common logarithm, and it can also be denoted by Lg of x. So again, Lg here means log to the base 10, and then the x comes in, and therefore it becomes log x to the base 10. So this is how a common logarithm works. And with the help of common logarithm, we can also find out the actual value of a logarithmic equation. For example, let's say we have 4 raised to x is equals to 7. Now we don't really know the value of x because this is not a perfect square or a perfect cube of 4. For example, if it would have been 4 raised to x is equals to 16, it is easy to figure out that x is 2, right? However, if it is something like 4 raised to x is equals to 7, what we do is we first convert it into a logarithmic equation, and it then becomes log 7 to the base 4 is equals to x. Now, the next step is to convert the base into 10. We can only find the logarithmic value of x, that is the actual decimal value of x when the base is 10. So therefore we use change of base theorem here. Change of base, and therefore we can write x as log um, yeah, we have log 7 by log 4. And if you remember, while discussing the change of base theorem, we had discussed that if we have the if we have the practically above number as the numerator and the base as the denominator, we can take the base as any number we desire. And what we desire here is 10. Therefore, x now is equal to log 7 to the base 10 divided by log 4 to the base 10. Now, in the next lecture or the next video, we will look at how to calculate this. Okay, log with the base 10 and a number. So for this, we require a logbook. So yeah, logarithms can be solved with the help of logbook. So that is it for this video, guys. I hope you liked it. Please stay safe. Thank you and bye bye.